In this video, I construct an example to demonstrate various concepts I introduced in the previous video. So this example is constructed with the symmetric group S4 and the dihedral group D6. For the S4 group, we have the tensor product expansion given by 3 cross 3 equal to 1 plus 2 plus 3 plus 3 bar. And for the dihedral group, we have the expansion 2 cross 2 equal to 1 plus 2 plus 1 bar. As a convenient basis, I use the matrices S, T, and U given here. The capital S, T, U are the generators of 3 of S4, and the small s, T, U are the generators of both 2 of S4 and 2 of D6. Of course, small s is trivial. And the flavor group contains the S4 group and 2 copies of D6 group. I call them acute D6 and grave D6, and 3 copies of Z2 group, Z2, acute Z2, and grave Z. Now I introduce the scalar field. The scalar field phi contains 6 irreducible multiplets. The first one is acute phi. It is a triplet in S4 and it is a doublet in acute D6. So for convenience, I have written this acute phi as a 3 by 2 matrix. And hat phi. This is a doublet in acute D6 and also a doublet in grave D6. So hat phi is a 2 by 2 matrix. Finally, grave phi. Grave phi is a doublet in grave D6 and a triplet in S4. Also, the fields acute phi S, hat phi S, and grave phi S are singlets. Now, let's see how these fields transform under the Z2 groups. So under the first Z2 groups, hat phi and hat phi S change sign. Others are invariant. And under acute Z2, hat phi S, acute phi S, they change sign. The other two are invariant. Finally, here you have the transformation under grave Z. So we have the scalar field and we have the symmetry group under which the scalar field transforms. The next step will be the construction of the potential. And I will construct the most general 4th order potential. So that is renormalizable potential. And you'll see that when you construct that potential, the magic happens. And if you analyze the invariants, you will see that there are a total of 39 invariants up to order 4. I'm not going to list these invariants here, but you may go through the paper to see the full set of invariants. In the rest of this video, I will show that the three assumptions that I introduced in the previous video will be satisfied for this potential V4. So out of these 39 invariants, 37 are invariant under the larger group G tilde F4. And what is this G tilde F4? If you compare it with GF, you see that instead of acute D6, I have two dihedral groups, acute D6A and acute D6B. And instead of grave D6, I have two groups here, grave D6A and grave D6B. And how is this larger group going to act on the fields? So that is given here. So acute phi is a triplet under S4 and a doublet under acute D6A. If you remember earlier, this doublet was simply acute D6. This time it is acute D6A. And here for hat phi, the first index is transforming under acute D6B. In the earlier case, that was simply acute D6. That means here I have two groups, acute D6A acting on acute phi and acute D6B acting on hat phi. So that is how this larger group acts on these fields. Similarly, look at the second index of hat phi. You have grave D6B. And look at the first index of grave phi, that is grave D6A. So here you have grave D6B and here you have grave D6A. So two different D6 groups. But previously you had only one D6 group, that was grave D6. So this is how the larger group acts on the field. And if you do the calculations, you can see that out of these 39 invariants, 37 of them are invariant under this larger symmetry group. Now, what are those two terms which are not invariant under this larger group? They are given here. These are those two terms, 38 and 39th term. So these terms are constructed with this following four multiplies. Let's look at them one by one. The first multiply, I wrote it as acute phi square 1 acute 2. So what does this notation mean? This is constructed with acute phi. It is second order and it is transforming as a singlet under S4 and doublet under acute D6. So that is the meaning of this notation, and its expression is written here. As you can see, there are two acute phi in it. So it's quadratic in acute phi. And these sigma 3 and sigma 1 are polymatrices. And this looks like a 1 by 2 matrix. And then let's look at the second multiply. So this is hat phi square. So it's quadratic in hat phi. And it transforms as a doublet under acute D6. and it is a singlet under grave D6. So that is this quantity. And this is a 2 by 1 matrix. And this term is like a dot product of these two. And you can see that this will remain invariant under the original group GF4. However, under this larger group, for this multiplet, the second index doublet, it is transforming under acute D6A, while the first index, the doublet, is transforming under acute D6B. So, this term is not an invariant under this larger group. And you can make similar arguments for the second term also. So the multiplets are given here. Regarding our assumptions, we have shown that two of them are true. We have a total of 39 terms. Out of these, 37 are invariant under the larger group G tilde 4, and there are two terms which are not invariant under the larger group. These terms are of the form X transpose Y. For the first term, this would be X transpose and this would be Y. For the second term, this would be X transpose and this would be Y. And these X and Y's, they transform as different representations under the larger group G tilde 4. Basically, I have shown that the first two assumptions are valid. Now, I will show that phi 0c given here is a stationary point of the potential V4 defined in some domain C, which is an open subset of R39. I will show this. Look at this expression for the stationary point phi 0c. Here, the dependence on the coefficients are only in these terms which I denote with V. So here you have acute VC, here you have hat VC, here you have gray VC, etc. These are in fact the norms of these irreducible multiplets. Other than these norms, every other degree of freedom of these multiplets, I have fixed it. I have not shown how this can be true, but for the moment, please bear with me. Given this state, let us study its symmetries. We can show that under these four group actions, under the larger group G tilde 4, this state remains invariant. Not only that, invariance under these group action fixes every degree of freedom of the state phi 0c except the norms of the theorems. Therefore, if you quotient out the norms, then in the resulting space, the point corresponding to this state will be isolated in the stratum with respect to the larger group G tilde 4. This is quite similar to the case that we discussed in the prerequisites video. There, we obtained a unit circle as the normalized space, and we obtained isolated red points. The only difference is that in that case, we had only one irreducible multiplet, whereas in this case, we have 6 multiplets and therefore 6 norms. In the prerequisites video, I had mentioned a theorem which states that if an orbit is isolated in its stratum, then for every potential, irrespective of the coefficients, this orbit will form a set of stationary points. That means in the normalized space, the point corresponding to this state will be a stationary point, whatever potential that you write. Now let us discuss the situation where these states are not normalized. Let C37 be the subspace of C obtained by the constraint that the coefficients of the 38th and the 39th terms are said to vanish. Let V437 and 50C37 be the restrictions of the potential and the field to C37. That means V437 is the potential invariant under the larger group G tilde F4. And C37 includes all values of the coefficients where the normalized space can be meaningfully defined. That is, where the norms of these irreps, all of them are non-zero. Here also, we will follow a procedure quite similar to the one that we followed in the preliminary video. We simply substitute the expressions of these irreducible multiplets in the restriction of the potential, then differentiate it with respect to the norms, and then equate them to 0. Those equations, if you solve, we obtain the values of the norms. There will be multiple solutions. Each of these solutions would correspond to a map 50C. If the norms of all the 6 irreps are real and positive, then that would be an example of this particular pattern of 50C. And the values of the coefficients that leads to real positive norms for all the 6 irreps for this solution would be the domain C37. Now let's go back to the third assumption. The third assumption is that the multiplets with which we constructed these last 2 terms, they should vanish for this state. And it's just a matter of simple substitution. We can show that they indeed vanish. Therefore, the stationary point 50C is equal to the restriction 50C to the lower dimensional space C37. In other words, the coefficients of these 2 terms play no role in determining the stationary point 50C. And the full domain C is C37 times R2. Now, over to the last video, where I will discuss the framework of the auxiliary group, in which elementary fields are used to construct effective fields. I will construct effective fields using the example field discussed in this video, and I will obtain the stationary points of the effective fields using this stationary point. And I show that the various concepts introduced in this paper lead to novel intrinsic constraints.